Next, we consider divergence and curl and Laplacian. Divergence is to collect the vector field, how much field are emitted radially from a point of interest. Suppose that we have electric charge, positive electric charge at this point, then electric field is coming out radially from this point. About this point, this side is a vector field that has a certain direction. On the other side, the vector field, the opposite direction. This kind of case will give the positive contribution to the divergence. For example, if it is vector field is steady flowing, then about this point, left hand side, right hand side, the magnitudes and directions are the same, then there is no divergence at all. Divergence becomes a negative when the field is coming in. Let's see. The definition. A vector field has three components, x, y, z components, and divergence is Cartesian first component, partial derivative with respect to x1, plus second component, partial derivative with respect to x2, and third component with respect to partial derivative with respect to the third component of x. So we add these three pieces together. So in short, if I apply Einstein convention for summation convention, round vi over round xi will be the component-wise expression for the divergence of a vector field. Next one is the curl. Curl's first component, second one component, and third components are written in this form. You will find that first component is round v3 over round 2 with positive sign. When 2 and 3 are flipped, exchanged, the sign is flipped with negative sign. In such a manner, Levi-Civita tensor is applied with the EI hat. Ith Cartesian component of a curl of a vector field is epsilon ijk, partial derivative with respect to xj of the third partial of the kth Cartesian component of the vector field V. Okay, if we write down curl V, ith component is E epsilon ijk derivative with respect to xj about kth component of vector field. Now we can substitute I equals 1, then this is composed of j and k are either 2 or 3. Either 2 or 3. So if it is jk equals 2, 3, then 2, 3, and 3, 2, then we have 3, 2. But because of this Levi-Civita tensor, we have negative sign on it. In a similar manner, second and third term can be expanded in such a way. Actually, curl has a, for example, this one has a non-vanishing curl. this vector field, just like the magnetic field coming from near the current coming out of this paper. This is a vector field at this point. If I follow that vector field, this is direction 1. If I follow the vector field, then we have additional component. There was no component at all for the transverse direction, that is a y direction. But if I go along the x-axis, then the vector increases along the y-axis. For example, this term. If I change the x1, then that results in the increase of x2 component. So vector field is the second component. And then, this 1, 2. This should be 2, 1. Typo. 2, 1. And then if I follow the direction of y2, what happens is vector field along the x-axis has the negative sign. So if I change the x2, v1 has negative sign on it. So in this structure, z component of this core of vector field v has this kind of form. Next one is a Laplacian. Laplacian is a del operator, the scalar product of del operator. That is, del operator is expansion of unit vector, and each component has the partial derivative along that axis. And another del operator is summed as a linear combination of the unit Cartesian vectors. We have repeated indices on the left, and we have another repeated indices pair on the right. And if I have double dummy variables, then I have to write different identifiers. Therefore, I used II here on the left-hand side and JJ here on the right-hand side. We know that Cartesian unit vectors are independent of positions, so partial derivative of this one vanishes. So we can safely pull out this one out of its derivative operator. Then if I combine this scalar product of two unit vectors, EI hat and EJ hat, I end up with the canonical delta because they are orthonormal. And then I have a double partial derivative with respect to xi and xj. Because there is a canonical delta, this I and j are combined together into a single index. Let me kill j to end up with double derivative with respect to xi. And here we have Einstein's notation. So what I have to do is just to sum this x1 squared, x2 squared, x3, the double derivatives all together. This is a Laplacian. Let us consider the double derivative of scalar function phi with respect to two Cartesian coordinates. Partial derivatives with respect to xi and xj, they commute. In quantum mechanics, we have momentum ith momentum, that operator is expressed in terms of xi. So if I compute the commutator pi pj, I have this one, h bar over I squared factored out, and commutator of partial derivatives, and this one is pulled out, expanded, and these two coordinates are independent, and the derivative of independent variables commute, so it is 0. So therefore we have these two operators commute. They have common eigenstates. This is true for any function that are differentiable to sufficient order. So xx double derivative with respect to x, and take the derivative with respect to y first, and then take the derivative later with x, and x first and y later. All of them are the same. And this is identity. Whether the right hand side is a scalar function or vector function or anything. We have a scalar function. Wait a second. Okay. So the derivative with respect to xi and xj, they commute. On the other hand, because they are commute, derivative with respect to xi xj and xj xi, they are the same. If I add these two pieces, they are the same, so it is doubled in comparison with this left hand side. So I multiply 1/2. Then it becomes manifestly symmetric form, ij symmetric. Suppose that I have a matrix that is symmetric. That means the transpose of that matrix is identical to the original matrix. Then aij is equal to aji, because the transpose, A transpose ij element is just a ji element. Alright. So if I have a symmetric matrix element aij, then it is 1/2 times 2 times aij, and 1/2 multiplied aij plus aji. Suppose that I have a matrix, just select A, the symmetric matrix, then I multiply Levi-Civita tensor with the epsilon ijk multiplied by Sijk, and we sum over J and K. Because S is symmetric, it is epsilon ijk, same vector with the Skj. If I add these two, it is doubled, so I multiply 1/2, so 1/2 epsilon ijk, Sjk plus Skj. So completely symmetric form, jk anti-symmetrical. We multiply these two vectors and sum over j and k. So I have epsilon ijk multiply sjk. Keeping this sjk the same, and I want to exchange the order of k and j. Then permutation gives epsilon ikj is minus epsilon ijk. So minus epsilon ijk is replaced with minus epsilon ikj. Right? Let me replace this repeated indices kk, and jj with a and b. So k is replaced with a, k is replaced a, and j is replaced with b, j is replaced with b. And then let me replace a with j, aa is replaced with jj, bb is replaced with kk. Now I return to epsilon ijk as kj. It is flipped. So because these two are the same, if I move this one to the left hand side, what I can get is epsilon ijk, sjk, and skj equals 0. So that gives this side is vanishing absolutely. Next, we consider the curl of gradient. We expect that curl and gradient, there are two del operators. Two del operators are there, and I have a single scalar field. So curl has anti-symmetric nature. Curl has the anti-symmetric nature, and derivatives are symmetric. So we expect that this calculation will be exactly 0. Here, I show you some example of using the repeated indices. If I write down a dot b, then I write aibi. Because I is a dummy variable, I can replace it with these repeated indices with something else. So I can still write it as ajbj. So if I want to compute the product of a dot b times c dot d, I use index I for the scalar product of a and b, so aibi. But once I use the index I twice, then I must not use that index I for the other repeated indices. So another example is just use the jj. So c dot d is replaced with the cj dj. All right. So let me return to the gradient. What I want to do is to compute the curl of the gradient. Curl of gradient. Gradient is ith Cartesian component of gradient is just partial derivative with respect to xi. And curl of gradient is, suppose that gradient phi is a vector field, so let me write it as A. If it were A, then ith component of this curl A is EI hat, Lebesgue tensor, epsilon ijk, and take the partial derivative with respect to the second index xj, and the vector field is ak. Now we substitute that the gradient of phi is actually the vector field A. So the kth component of A is the partial derivative of the scalar field phi with respect to xk. Substituting this result into ak, we find that the ith component of curl gradient phi is a Lebesgue tensor epsilon ijk, and this derivative, partial derivative with respect to xj, and then partial derivative with respect to xk of a scalar field phi. We can collect this one derivative as we have done before. We have this one, and the same thing with the indices exchanged because they are symmetric, and because we have double result, so we multiply 1/2. We find that this is epsilon ijk anti-symmetric, this jk symmetric. The result will be 0. Let us look at the detailed calculation more closely. Epsilon ijk, xk, xj is, I can replace the dummy indices jj, kk with kk, jj. And then it becomes derivative is exchanged with the k first and the j next. But I have epsilon ikj exchanged. Let me return to the epsilon ijk. Then I need a single permutation of k and j. I have negative sign on it. So kj derivative, this term, multiplied by epsilon ijk is actually negative sign. So this becomes minus so this is exactly 0. Curl of gradient is always 0. Next, we consider divergence of curl. Divergence of the curl of a vector field is again exactly 0. Let's see divergence of curl V. Let me say this is a vector, call V to be a vector field. Then this is divergence, and divergence is partial derivative the ith component with respect to xi and sum over I. However, A is a vector field that is equivalent to curl V. So what I have to do is find out the explicit value for the vector field A's ith component. The ith component of vector A is epsilon ijk, and derivative with respect to xj of vector field of a kth component. So if I substitute this AI in here, I find that over vector epsilon ijk, and this xi derivative is here, and xj derivative is here, and multiplied by it is to be operated to the kth component of the vector field. Now again we have ij summed over. They are all repeated indices. This epsilon ijk has completely anti-symmetric nature under exchange of ij, and this derivative, product derivative, double derivative, has symmetric form under exchange of ij. Therefore, anti-symmetric times symmetric summed over the repeated indices is equal to 0. Therefore, divergence of a curve is always 0. So divergence B equals 0 for the magnetic field. And magnetic field, once the magnetic field is expressed in terms of curl of a vector field, if I substitute this in here, divergence curl A. So regardless of this vector field nature, it is always 0. It is identity. Next step is to compute the we can check this calculation by an explicit calculation. So curve can be computed in an explicit form. The first component of a curve V is using epsilon ijk 1, 2, 3 and 1, 3, 2. 1, 2, 3 is an even permutation. So we have a positive sign on it for round V3 over round X2. Second piece has odd permutation. So epsilon 1, 3, 2 has the negative sign. So we have minus sign in here. And second term, the second Cartesian component of the curve V is 2, 3, 1 is a positive permutation. 2, 1, 3, it's a negative permutation. Positive permutation has around V1 over around X3. The negative permutation has around V3 over around X1 has a negative sign on it. And that the third component can be computed in a similar manner. That's round V2 over round X1 minus round V over round X2. If I take the divergence of this vector field, what I get is this is the first component of the vector field, second component, and third component. The divergence collects the partial derivative of the first piece with respect to first component. Second vector field component with respect to second Cartesian component. And the third one by the third Cartesian component. We find that derivative with respect to x1 and x2 appears here on the x of V3. And x1 and x2 again appears in here on x3. But this one has the positive sign and this one has a negative sign. So these two cancels. And about 1 and 3, derivative with respect to 1 and 3 has negative sign on it on the second component V2. And where where is this counterpart? In here. It's x3 and x1 on v2. But this one has a positive sign instead of the negative sign. So these two cancel exactly. Remaining pieces are here. Derivative on v1 with respect to x2 and x3, and v1 with respect to x3 and x2. So this one negative and positive. They cancel exactly. Next step is to compute the curl. Let us compute the curl of a vector field V. Curl of a vector field V can be computed in a similar manner. So the ith component, ei hat, is the unit vector, and the ith component has a coefficient, the component epsilon ijk with derivative with respect to j, and this is curl V. Curl V is a kth component. Now, the kth component of a curl V can be expanded in terms of epsilon klm, and with respect to the derivative with respect to xl on the mth component of the vector field. Now we have two Levi-Civita tensors, epsilon ijk here and epsilon klm here. But I can shift this index k to the left. If I exchange it with j, I have negative sign. And then if I exchange one more time with I have k in front and jk later. So because I have exchanged it twice, I have sign twice, so I have positive sign. So this is positive. And then I have two Levi-Civita tensors summed over a single index k. There is a formula listed below. And then remaining pieces are I hat, ei hat, xj derivative, and xl derivative, and vector field Vm is here. If I sum over k, then indices should be collected into two pieces. One is even permutation, the other is odd permutation. Sure, even permutation and odd permutations are the same, and even odd permutation and odd even permutations are different. So that happens. The positive sign appears when I and L are the same and J and M are the same. Negative relative permutation appears when I is equal to J, M, and J equals to L. So this derivative operator's unit vector and the component are copied in here. I can make use of these chronicle deltas to remove unnecessary indices. So with delta IL, I can replace, after summation over L, L is replaced with I. L is this guy is replaced with I. Delta JM, M is replaced with J. M is replaced with J. And remaining pieces I copied. EI hat and XJ derivative is here. Minus sign is here. I have EI hat and XJ derivative. And then because of this delta IM, Vm is replaced with Vi, and because of this delta JL, this XL is replaced by XJ. Now, I appears this operator and this operator, they commute. So let me move this one to the left. Then EI hat means partial derivative with respect to xi. That means just the gradient operator, just the del operator itself. And the remaining pieces, xj derivative for vj and sum over j. That is just divergent of v. Next one, I have xj squared. And actually I can move this one to the right because it is a unit vector, the constant unit vector. It is independent of it vanishes if I take the partial derivative. So this is just a vector. So as a result, what I obtained for the core vector field is the gradient of divergence V minus Laplacian of a vector field. These are all very useful for electromagnetic calculation. Okay. Next, we compute core of cross product of A and B. These are computing in here. Let me record the momentum operator. Momentum operator, x component momentum operator px is a partial derivative with respect to x multiplied by the h bar. H bar is a Planck constant over 2 pi. H bar over I, partial derivative will be the x component, x derivative. If I use ith Cartesian component instead of xyz variable, then the ith Cartesian momentum component operator will be expressed in terms of pi, and pi is h bar over I. This pure imaginary number I is not an index, and partial derivative with respect to the ith Cartesian component. Commutator of pi and pj is h bar over I, and partial derivative with respect to xi and xj. I can factor this h bar over I out twice to find that commutate. This is h bar over I squared with the commutator for the xi derivative and xj derivative. You know, xi derivative, xj derivative, they commute. This one will vanish. Therefore, the momentum operator pi and pj commute. Thus, they have a common eigenstate. Next, we consider the computation of curl of A cross B. Curl of A cross B involves EI, ith component will be Levi-Civita tensor with the xj's partial derivative, and the kth component of the vector field. That vector field is A cross B. A cross B, so kth component will be epsilon KLM BL AL BM. Okay, repeated Levi-Civita tensor appears here too. So I copy EI hat epsilon ijk is replaced with epsilon kij after permuting this k twice, exchanging with the j, exchanging with I. I have a twice permutation, that means a positive sign on it. And then this epsilon KLM is copied in here. And I have a partial derivative with respect to xj, and ALBM is copied in here. You know, this EI, same. And the sum over K, the product of two Levi-Civita tensors will give this product linear combination of two products. So it is I and L and J and M. I and L, J and M are the same, then it is positive. And I and M and J and L are the same, then that gives a negative sign. And I have a derivative in here. First, IL means delta IL means I replace this L, replace this L with I. That means AI is here. JM, I replace this M with J. I replace the M with the J. And I have derivative as it was. And I have negative sign on it. EI copied, XJ copied, and then IM. This M is replaced with I. JL, this L is replaced with J. Okay. And then I apply the derivative rule for the product. Derivative of A times B and A times derivative of B. Derivative of A times B and A times derivative of B. So substitute this formula, then I get EI hat derivative of A and no derivative for B, and derivative of B and no derivative for A, minus EI derivative of A with respect to xj and no derivative for B, minus EI derivative of B and no derivative for J. Okay? Now, I have this BJ comes here, and BJ and derivative J. And the EI is a constant, so I can insert inside the derivative. So that means EI is an A vector. Next step. So EI-BI. A is pulled to the left, so it becomes A vector. And then this is BJ/XJ derivative. Divergence of B. So this one is divergence B. So A divergence B. So combined, it's EI-BI. This is B vector. And then AJ/XJ divergence of A. I minus EI will be combined with B, and AJ, XJ, is not a divergence, instead A dot del. Finally, this one is also just like what we did for the derivative multiplied by AJ. This one is A dot del instead of divergence A. So B dot del. So B dot del A plus A divergence B minus B here. A dot del B, B divergence A. So this is the final result. Wait a second. Next we study the total differential of a function. For example, if we have a scalar field is a function of position. Position has three components. So variables are x1, x2, and x3. And if I have a multivariable function, total differential of that function is computed by making use of the Taylor series expansion. Taylor series expansion about x by a shift delta x1, delta x2, and delta x3 can be computed in this way. If I subtract the original value, then the leading piece will be proportional to delta x, delta x2, delta x3. Overall coefficient for delta x1 is a partial derivative with respect to x1. The coefficient for delta x2 will be the first order partial derivative with respect to x2. And the coefficient of delta x3 will be the partial derivative with respect to x3. If I expand in to higher orders, is 2 factorial, second order derivative, delta x1 squared, and so on. And delta x has the magnitude h, and we take the limit h goes to 0. Then all the other pieces of higher orders in delta x squared or higher will be collected in here. In the limit delta x goes to 0, this one becomes the dominant contribution. So this is a finite change, but infinitesimal change can be expressed as d phi, and that d phi is a sum of the ith component gradient multiplied by the ith component of the differential dx. In case this phi is a function of time, then this one is independent of time. So this is a so-called time-independent field. And in case phi is a time-dependent field, I have this contribution that appears for the time-independent field, and partial time derivative of that phi multiplied by differential of time dt. We remember the product function's differential is dxy plus xdy. If I replace x and y with a and b, then this dab multiplied with adb. Suppose that we have a vector. The differential of a vector can be computed as follows. Vector A is a linear combination of I component, and the overall vector is EI. And if I take the differential, this unit vector is a constant. DEI is constant. So we end up with a single term, EI multiplied by differential of I component. In case this vector field is time dependence too, this differential is just round AI over AJ dx, and here time derivative, here multiplied by dt. So the first piece, the second piece, I can vector this, include this one into in here. I have a vector A. Vector A is time derivative multiplied by time differential dt. And first term, dxj, infinitesimal differential for xj, can be moved to the left, and ei will be included into vector A. So this becomes vector A. And this one can be written as a scalar product of differential dx and gradient operator. So this is the result. So it is shown here. Vector differential of a vector time-dependent vector field, total differential of a time-dependent vector field can be written in this form. Next, we consider the continuity equation. Continuity equation involves the current density. Current density here, the volume current density. Volume density rho is a time-dependent field. And the density is mass per unit volume. In case the volume, the density varies depending on position, then we can take the differential rate. So dm over dv. This is infinitesimal mass, and it contained in the infinitesimal volume dv. Then we define the current density. Current density is a density multiplied by the velocity of the fluid, or particle current. All right. Let us consider, let's compare the meaning of this current density in comparison with the current. Current is actually defined by the scalar product of current density multiplied by a cross-sectional area A, and is equal to, sometimes it is charge, depending on problem, sometimes it's mass per unit time. So there is a cross-sectional area A, and cross-sectional area A vector is defined by its magnitude is area itself, and direction of this area vector is perpendicular to the surface. We can choose either, there are multiplicity, this direction or that direction. So there are two choices. But usually, if we want to compute something, we must define the direction of the surface. Usually, if I want to compute some differential area on a closed surface, usually the direction of the surface is toward outside of that volume, which the closed surface is surrounding. All right, this J dot A has a current density J, magnitude, and the cross-sectional area A, magnitude, multiplied by the angle cosine theta if this current density and area vector has some finite angle theta. So we have J, in case we have the angle theta, the theta dependence is simple, this is just cosine theta. In case we have angle theta equals to 0, then we would have JA equals current I, and that is delta Q over delta T. Okay, if I divide both sides by area, cross-sectional area A, the current density is charge divided by cross-sectional area times delta T. On the left-hand side, on the definition, if we consider the definition of current density, left-hand side, rho equals delta Q over delta V. And V is a delta X over delta T. So, left-hand side, rho V is delta Q over delta V multiplied delta X over delta T. On the other hand, the right-hand side, delta Q, A over A delta T. So here, delta Q cancel, and the delta T cancel. What we find is delta X over volume. You know, the volume spent by delta X during delta T, so it's delta T equal V times delta T. So this volume is cross-sectional area times delta X. Okay, so we can understand the meaning of the current density. Next, we consider the flux. Current J is flowing in the space, and we have X, Y, Z axis, and we'd like to consider a small volume whose x-axis width is delta x1, delta x1, delta x2, and delta x3. If I want to compute the flux, that is current, just like flux is equivalent to the current density and cross-sectional area scalar product. We have, if we consider these 6 surfaces, all 6 surfaces are along the x-axis positive direction, and this area is a delta x2 and delta x3, and direction is E1 hat. And the other one, and we call this as a delta sigma plus vector. On the opposite side, we have delta sigma minus. This is proportional to minus E1 hat, opposite direction. And magnitude is the same, delta x2, delta x3, delta x2 and delta x3. In a similar manner, y-axis, we have positive direction and negative direction, 2 surfaces toward the positive and negative side. And then along the z-axis, toward the positive z-axis and negative z-axis. Okay. So sigma 1 plus minus is plus minus E1, delta x2, delta x3. So this one can also be written in the form plus minus E1 hat, delta V over delta x1. And in general, plus minus EI hat, delta V over delta xi. Okay, if I want to compute all the current coming out of this volume, I need to compute this flux on x1 plus minus, sigma 1 plus minus, sigma 2 plus minus, and sigma 3 plus minus, all 3 cases. We first compute the x component. In the case of x component, sigma 1 plus is toward E1 plus direction. Sigma 1 minus is toward the E1 minus that direction. And current is multiplied. We have a J three-dimensional vector. However, J dot sigma 1 collects only the first component of current. This one also. Therefore, if I compute the flux on the sigma 1 plus and sigma 1 minus, it is parallel to the x-axis and anti-parallel to the x-axis. I have positive sign on it, and this is along the x-axis. So E1 contribution, J1, first component is collected. But the position of this surface is placed at x plus E1 hat 1 half delta x1 here, plus 1 half delta x1 minus 1 half delta x1, where this x is the central point of this volume. We recall that the area of the sigma 1 plus and sigma 1 minus are delta x2 and delta x3. That can be expressed in terms of volume divided by delta x1. So substitute this area in here. Now we find that this one is a delta V volume, and delta x divides the difference of J1. That means in the limit delta x goes to 0, it is a partial derivative with respect to x1. So x1 is a partial derivative with respect to x1. If I sum these are two surfaces along the x-axis, we have two more pairs. Along the y-axis, that will be J2's partial derivative with respect to x2, and J3's partial derivative with respect to x3. So sum of this. So this one means this region, flux passing through all these surfaces, 6 surfaces. And we say this is a closed surface. Now, this flux is just J dot d sigma over a closed surface. This circle means a closed surface. Flux is just a J dot area vector. So J dot d sigma equals divergence of J. This is divergence. And if I integrate, sum this one over a region, divide a region into many pieces, and then sum them all, then I end up with this relation. And this one is called divergence theorem. In the limit xi goes to 0. So this one, this is the summary. Next one, consider the flux phi. If current is coming out of this region, sum of flux will be positive. But in that case, the contents inside the volume will leave the space, so mass will decrease. In case the flux is negative, the mass flow is coming in, charge flow is coming in. Then delta M or delta Q it will increase. So it is a kind of conservation. So flux Cj dot A must be the same as a mass time rate of mass change with negative sign. Is coming from the current density, definition of the current density. Well, J equals rho V. J dot A equals rho V delta T delta X dot A. Aha. Delta X dot A delta V. Okay. Here, the mass is mass change. Negative sign of mass change, it will, after taking the time derivative, it will be, for a constant volume, it is a time derivative of density multiplied by volume. Finally, we end up with the continuity equation, divergence J. Divergence J multiplied by volume was flux, sum of fluxes, and that was the equivalent. So flux divided by volume should be this time, negative time derivative of density. So this is conservation of mass and conservation of charge, and this continuity equation. Next, we consider the so this, in summary, this is divergence theorem. Finally, we consider the Stokes theorem. Stokes theorem involves a vector field who has a non-vanishing current. For example, if I have non-vanishing current, I have a magnetic field surrounding that current. This current, magnetic field does not diverge, instead it rotates. If this is the direction of magnetic field at this point, if I shift by dx, delta x along the x-axis, then the magnitude of the magnetic field along the y direction, so B2, increases as x1 increases. And if I increase the x2, increase the x2, the magnetic field along the x-axis decreases, minus B1. B1 is to the left hand side here. B1 was along the positive side. So curl has the nature that increasing component of perpendicular component in comparison with the displacement. So we apply a very similar calculation as we have done for the divergence calculation. We consider a surface x, y, z, and is A, B, C, and D. We compute the line integral of vector field that dx along this rectangular closed path. This is a closed path. This circle means a closed contour, closed path. So AB, BC, CD, DA. These, if I add these 4 components, we will find the closed contour. First of all, 3 and 5. 3 and 5 means you know this is along for example AB. I have a XY, AB, AB is along the y-axis, along the y-axis, from, this is plus direction, plus direction, and here, okay, here x is fixed, y comes from minus half of delta, and y end up with, so this is x comma y half of delta to x comma y plus half of delta. So I think that the figure is different from this calculation. So we need to correct the figure. Anyway, in such a way, I compute the line integrals, all 4 line integrals. And you will find that all 4 integrals comes from the some difference. Because our time is not enough, let me summarize the result, only the result. The Stokes theorem is that the line integral along a closed loop is a curve multiplied by as a scalar product with the area. That means this is a line integral. If I compute the vector dot dx along the closed loop, the result is curve vector on the surface with area, and this is the area S, and this is a contour, closed contour enclosing this surface. That means C equals around S, surface boundary. Okay, this is the Stokes theorem. Alright, that's it for today.